In this video, we'll discuss elementary matrices and LU factorization. So one of the motivations behind factoring matrices is that typically matrix multiplication is a somewhat complicated calculation, right? So when multiplying, say, two n by n matrices, each entry of the result requires n separate calculations to do the dot product. And because there are n squared entries in the matrix, in total for an n by n matrix, typically you need n cubed separate multiplications to do the calculation. So one of the ideas behind factoring matrices into simpler matrices is to try to reduce the amount of multiplications you need to do because you get the matrix into a simpler form. However, we'll see factoring matrices is a little bit more complicated than factoring numbers because matrix multiplication is a more complicated operation. Before we get to LU factorization, we're going to first look at elementary matrices. So in terms of the row operations that can be done to a matrix, there are three elementary row operations. So the first row operation is interchanging two rows of a matrix. The second row operation is multiplying a row by a non-zero constant. And the third operation is adding a multiple of a row to another row. So basically, these three row operations mimic the different operations you do to a system of equations, and you can transform a matrix into a row equivalent one by applying one of these elementary row operations. Okay, so those are the elementary row operations, and an elementary matrix is just a matrix that's obtained from the identity matrix by applying one of these three row operations. So for example, say I'm working with 3 by 3 matrices. Okay, so this is the 3 by 3 identity matrix. And if I want to obtain the elementary matrix obtained from swapping two rows, say for example if I want to swap row 1 and row 3, right, so I'd take the identity matrix and switch those rows. Right, so I take the identity matrix and I switch row 1 and row 3. So row 3 goes into row 1, row 2 stays the same, and then row 1 goes into row 3. And so this is the elementary matrix you get when you swap rows 1 and 3. And we can see with the other kinds of row operations, you just follow a similar procedure, right? So if I want to take the row operation of multiplying row 2 by 1/3, again I take the identity matrix. First row stays the same. Second row I multiply by 1/3. And the last row stays the same. And finally, this kind of row operation, I'm taking -3 times row 1 and adding it to row 2. So again, to get the elementary matrix, I do that operation to the identity matrix. Okay, so here row 3 is staying the same. Row 1 also stays the same. So the only thing that's changing is row 2, right? So what's happening is I'm taking row 2 plus -3 times row 1 and putting it into row 2. So -3 times row 1 is a -3 in this entry. I'm adding it to row 2, so this makes it this entry a -3. This will be 0 plus 1, which is 1, and this would be 0 plus 0, which is 0. Okay, so this is the elementary matrix for this row operation. Okay, so the idea behind the elementary matrix is that when you're applying these row operations to any other matrix, it's the same as taking the elementary matrix for that operation and multiplying A on the left. So for example, say I take this elementary matrix that swaps the first and the third row, and I multiply it to A. Right, so if I do the matrix calculation, right, so first row times the string will pick out the third row, so -2, 1, 1. Second row times this matrix will pick out the second row, and then third row times this matrix will pick out the first row. And you can see that the result of this matrix multiplication is the same as if I applied this operation to the matrix A, right? So swapping the first and the third row, you can see is exactly this thing. And so we can look at the other two examples and the same thing occurs, right? So if I take the elementary matrix and I multiply it on the left, by A, so this row times this matrix will pick up the first row. This row times this matrix will take the second row and multiply by 1/3. And then this row will pick out the third row. And again, the resulting matrix is if you just applied the row operation directly to the matrix A. And then finally, we see that's also the case in the last example. So this row times this matrix will pick out the first row. Now this row times this matrix, right, so it's -3 plus 3 is 0. Then -9 plus 2 is -7. And then 6 plus 5 is 11. And this will just pick up the last row, -2, 1, 1. And again, it's the same thing as if I multiplied -3 times this row plus this row, right? Because this is -3 plus 3 is 0. And then -9 plus 2 is -7. And then 6 plus 5 is 11. Okay, so again, the basic idea behind these elementary matrices is we can relate the row operation to matrix multiplication. And the elementary matrix, again, is obtained by doing the row operation to the identity matrix. Okay, so now that we have an idea of what elementary matrices are, we'll see that elementary matrices themselves are invertible. So the reason is because the elementary matrices are coming from the three row operations, and each of the three row operations can be undone. So one thing that's good about the elementary matrices is it's fairly easy to determine what the inverse matrix is. Again, basically because it's just relating to how you undo each of the row operations, right? So the inverse of swapping two rows is basically just swapping the same two rows back. The inverse of multiplying a row by a constant is multiplying the same row by the reciprocal, right? Basically just to cancel it out. And the inverse of adding k times one row to another is subtracting k times that same row to the other row. Okay, so let's look at the three elementary matrices that we discussed previously, right? So this first elementary matrix was the one where you swapped row 1 and row 3, right? So to undo that, you would just swap back row 1 and row 3. So the inverse of the elementary matrix where you swap two rows is basically the same matrix itself. So the inverse of this matrix is the same matrix. Okay, so this second kind of matrix was the one where you multiply a row by a constant, right? So this one is you're multiplying the second row by the constant a. So to undo that, you would multiply the second row by the reciprocal. And the reciprocal of a is 1 over a. And then finally, this last type of matrix is you're multiplying k times the first row and adding it to the second row. So to undo that, you would just subtract k times the first row from the second row. Okay, so subtracting k would give you a minus k in that entry. And then all the other entries stay the same. And you can check by doing the matrix multiplication that these are actually the inverse elementary matrices. Okay, so again, it's fairly easy to determine the inverse matrix to an elementary matrix. Okay, so we have all the tools now to put together what we want to be as the LU factorization. So basically the idea behind LU factorization is that we can apply a sequence of row operations to a given matrix A to produce an upper triangular matrix U. And so a matrix is called upper triangular if all the entries below the main diagonal are all zeros, right? So this is an example of a 3 by 3 upper triangular matrix, right? So on the main diagonal you can have anything, and above the main diagonal you can have anything, but as long as every entry below the main diagonal are zeros, then it's upper triangular. Okay, so what's going to happen is that we change a matrix A to have this form by applying a sequence of row operations. And if we keep track of the elementary matrices associated to these row operations, so say the sequence is E1, E2, and then all the way up to EK, right? So say there are K row operations. So from what we discussed before, applying row operations is the same thing as multiplying on the left by an elementary matrix, right? So you're first multiplying on the left by E1, and then you're multiplying on the left by E2, and then you're multiplying on the left by E3, and so on, right? So that's why the elementary matrices are written in this order, because you're multiplying on the left in sequence. And then applying these elementary matrices to A produces our upper triangular matrix U. And then if we solve this equation for A by multiplying the inverses for the elementary matrices, they will appear in this order. Okay, so if you remember, the inverse operation reverses the order. That's why the inverse elementary matrices appear in this order. And so you can see that so if we ignore this type of row operation and focus mainly on this type of row operation, this type of row operation is lower triangular, right? And so if you multiply a bunch of this kind of matrices together, then the result will be a lower triangular matrix. Right, so basically we're gonna focus on matrices A that you can apply the third type of row operation to. So we're gonna strictly be sticking to the third type of row operation when we're doing LU factorization. Okay, so let's take a look at an example where we go through the whole process of LU factorization. So in this example, I'm going to try to find the LU factorization of this matrix here. So let's call this matrix A. So we need to eliminate the entries below the diagonal, right? So it's going to be these three entries here by applying a series of the third type of row operation, right? So the row operation where you're adding a multiple of a row above to one that's below. Okay, so as we're doing elimination, right? So you should eliminate one column at a time, right? So first we'll focus on the first column. So we're going to use the first row, and specifically the entry in the first entry in the first column, to try to eliminate below that entry. So these two entries are going to be eliminated by this entry here. Okay, so if I ask myself, how can I eliminate the 2 using this entry here? So I need it to be -2, right? So -2 times the first row, adding it to this row will cancel out the 2 here, right? So that's the operation I want. So the operation is -2 times row 1 plus row 2 goes into row 2, right? So we're eliminating this entry from row 2. Okay, so now let's do the calculation. So -2 times the first row, right? So that's -2 plus 2. So first row stays the same. So -2 plus 2 gives me 0, so that's eliminated. And -2 times this will give me -6. -6 plus 5 is -1. And then -2 times this is 0. 0 plus a -1 is -1. And then third row stays the same. Okay, so that's the first row operation. So we're going to need to keep track of the elementary matrices, right? So this is the first row operation. And so the first elementary matrix, so it's the third type, right? So the entry matrix will look like this. We're doing -2 times the first row and adding to the second row. So a -2 goes in this entry here. Okay, so that's the first elementary matrix. Okay, so now let's continue the elimination process. Right, so we're still using the first row and trying to eliminate this entry here. So to cancel the 3, I need a -3. Right, so I need -3 times the first row plus the second row, plus the third row, because we're eliminating third row here, going into the third row. Okay, so calculating the resulting matrix, what do we get? So first row stays the same, second row stays the same, and then, okay, so now we calculate the third row. So -3 plus 3 is 0. -9 plus a -2 is -11. And then 0 plus a -4 is -4. Okay, so that's the second row operation, and then the elementary matrix for that. So you're adding -3 times the first row to the third row. So -3 goes there. Everything else looks like this. Okay, so now you can see the entries below the diagonal in the first column are complete. Right, so now I want to continue on to the second column. So I use the second row to eliminate below the diagonal in the second column. Okay, so I need to eliminate the -11 here with the -1, right? So I need to add 11 to cancel it out, right? So to turn into a positive 11, I need to multiply by -11, right? So it's -11 row 2 plus row 3 will go into row 3. So first row stays the same, second row stays the same, and then third row we're calculating, right? So -11 times -1 is a positive 11. Positive 11 minus 11 gives you 0. And then -11 times -1, again, is positive 11. Positive 11 minus 4 is 7. Okay, so this is what we get. So now you can see that this is upper triangular, right? Because above the diagonal, I can have anything, but below the diagonal is all zeros. So this is my matrix U. And the third elementary matrix was coming from here, right? So it looks like this. And we're doing -11 times row 2 plus row 3. So I got a -11 here. Okay, so let's call this matrix A1, this matrix A2. Right, so basically we started with matrix A and we turned it to matrix U by this sequence of row operations. So in terms of the elementary matrices, right, so I'm taking A and I'm multiplying on the left by these elementary matrices, right? So the matrix equation is I'm starting with A, then I apply the first elementary matrix, then I apply the second elementary matrix, then I apply the third elementary matrix, right? So individually on the left, and then the result of this is I produce U. And then so now solving this for A by taking the inverses, right? If you remember, it reverses the order of the elementary matrix, right? So this will say A is equal to E1 inverse, E2 inverse, E3 inverse times U. and multiplying these together will give me my matrix, my lower triangular matrix. Okay, so we need to know the inverses of these three elementary matrices, right? But that's not too difficult to get, right? So what is E1 inverse? So it's just essentially the same matrix, but taking the opposite of the entry here, right? So that becomes a positive 2. E2 inverse again is essentially the same matrix, but I take the opposite of this entry here, so that becomes a positive 3. And then E3 inverse is again essentially the same matrix, but I get a positive 11 here. Okay, so those are my three inverse elementary matrices, right? So if I multiply them together, I get my L, right? So let's calculate that. So L is equal to, right? So again, I already have my matrix U. This is U. L I can obtain by multiplying these three inverse matrices together, right? So E1 inverse first. So E1 inverse, then E2 inverse, then E3 inverse. So multiplying together, what was E1 inverse? It has a 2 there. And then E2 inverse has a 3 here. And then E3 inverse has an 11 here. Okay, so what do I get as my lower triangular matrix? Right, so you can see that so let me multiply these two first, right? So what is this? I'm running out of space, so let me do it a little bit smaller, right? So multiplying these two, this is 1, 0, 0, and then this will give me a 2 here, and then a 1 here, 0, and then this will pick out the third row, so 3, 0, 1 here, and this matrix stays the same. Okay, so now multiplying these two matrices together, this will be my L. So what do I get? So this is just the first row, and then this will give me a 2 here and a 1 here and a 0. And then this row times this gives this going to be a 3 here. Then it picks out the 11, and then it picks out the 1. Okay. So this is my matrix L. And to make sure that we have the L and U correct, right? So this should be the factoring of A, right? So if I multiply L times U, I should get back A. So L times U is equal to A. Right, so what was L? It's 1, 1, 1, 2, 3, 11, and then zeros here. What is U? U is this, so 1, negative 1, 7, and 3, 0, negative 1. And then if I multiply these two things together, what do I get? Okay, so this just picks out the first row, so 1, 3, 0. Then this would be 2 here, and 6 minus 1 is 5. 0 minus 1 is negative 1. And this is a 3. 9 minus 11 is a negative 2. And then negative 11 plus 7 is negative 4. So that's L times U. And then this is the same as A. So 1, 1, 3, 0. 2, 5, negative 1. Then 3, negative 2, 4. And so this checks out. Okay, so we have our LU factorization. And this is the entire procedure to obtain it. Okay, so this last page is just a quick discussion of what it means for a square matrix to be idempotent. Right, so a square matrix is called idempotent if you square a matrix and you get the same matrix back. So before we get to matrices, if you think about it in terms of just real numbers, the idempotent property isn't really that interesting for real numbers, right? Because the only real numbers that have this property is either 0 or 1, right? Because 0 squared gives you 0 back, and then 1 squared it gives you 1 back, and then none of the others none of the other real numbers have this property, right? But because matrix multiplication is more complicated, you can see that you can have various non-trivial matrices that have this property, right? So in this example below, right, so here this is just a trivial example where if you take the identity matrix and you multiply it by itself, you get back the identity matrix, right? So the identity matrix is idempotent, but again, this matrix isn't that interesting. Same for the 0 matrix, right? So the 0 squared is equal to 0, right? So the 0 matrix is idempotent. But again, these two examples aren't that interesting, right? But here, I give you this matrix here, 3, negative 6, 1, negative 2. It's a 2 by 2 square matrix, and if you multiply it out, you can see that here the resulting matrix is the matrix itself, right? So this matrix is idempotent, right? So you can do the calculation. You get 9 minus 6 is 3, then negative 18 plus 12 is negative 6, then 3 minus 2 is 1, then negative 6 plus 4 is negative 2. So this matrix is non-trivial, and it is idempotent. But in general, most matrices are not idempotent, right? So here, if I take this matrix here, right, and then I square it, so meaning I multiply by itself, you can see that the resulting matrix, so 3 other entries are the same, but this entry is not the same, right? So I get it's minus 1 gives you a negative 2 here, which is not the same as the original matrix. So this is not idempotent. Okay, so I mean, so you can try to play around with this a little bit and try to find other non-trivial 2 by 2 matrices that are idempotent. But again, most matrices are not idempotent.